Okay, let's just go over some definite integrals, just kind of remind you how they work and really what they represent here. So if we look at this first definite integral, we're integrating 4x plus 1. Again, that's the integrand, and we're going to integrate it from 1 to 5. So go ahead and do the integral. The integral in this case would just be the power rule. If we increase the power by 1 and divide by the new power, we're going to get 2x squared plus x. And I think most people are going to draw some vertical line and then write the bounds. And what you're going to do here is you're going to evaluate this from 5 to 1. And so that means plugging in 5. So 2 times 5 squared, that's 50. So we get, what, 55? Minus plugging in 1. When you plug in 1, you get 3. And so 55 minus 3 is 52. Again, when you think about the definition of a definite integral, if you integrated from a to b of some function, it's equal to the antiderivative at b minus the antiderivative at a. And that's what I did there. I integrated 4x plus 1 and got 2x squared plus x, and then I plugged in 5, and I subtracted plugging in 1. Again, this vertical line is just talking about the bounds. Plug in the upper bound, subtract plugging in the smaller bound. And that's what I did. Okay, and again, what is this doing? Well, when you integrate, one of the ways to interpret it is you're finding the area underneath that curve. And so if we looked at that curve, 4x plus 1, that's just some linear function. Oh, it would look something like this. And if you integrated from 1 to 5, you'd be finding this area. Okay, and we can check that. We know what these points are. Well, when x is 1, that's 5. So this is the point 1 comma 5. And then this is at 5, right? Our upper bound, our upper x value is 5, and that's 5 comma 21. Okay, so we're finding this area. Well, that is really just a trapezoid. This is a width of 4. And so we know that a trapezoid is 1/2 times the height. And then the height is 4 in this case, right? This is the height of the trapezoid, kind of pretend flipping it on its edge. And then times b1 plus b2. So that'd be 1/2 of 4, which is 2. And then 2 times 26. Boom, 52, right? The area under the curve is the same thing as the integral. Okay, let's kind of do these other ones. So the integral of sine is negative cosine x, and we evaluate from 0 to pi, right? So if we plug in pi here, we get negative, right? Negative cosine of pi, but that's negative 1, minus plugging in 0, so negative 1. I know that's a whole lot of negative signs in there, but it's just that you're going to get a negative from the cosine, a negative because you subtract here, but then cosine of pi is also negative 1, so we get a lot there. Okay, so this is 1 plus 2, and we get 2. And what does that say? That says that the area under the sine curve from 0 to pi, right, this area is exactly equal to 2, which is kind of cool. So you now know that the area under one arc of either sine or cosine, because they're the same function, just shifted a little bit, is equal to 2. Okay, how about this one? So the integral of 2 e to the x, so the integral of e to the x is just e to the x. Those are the easiest ones. So it's just 2 e to the x, and then evaluate from 0 to the natural log of 5. So that's just 2 e to the natural log of 5, right? Minus, and then plugging in 0, 2 e to the 0. Well, e to the natural log of 5 is just 5. 5 times 2 is 10. E to the 0 is 1. 2 times 1 is 2. So then that is 8. And again, what we're saying here is that the area under the curve, so 2e to the x, some exponential start there at 2, and it kind of zip that way. And so if we stopped at the natural log of 5 and looked at that area, it would equal 8. All right? And then we have this last one, the integral of 1 over x, right? Or the antiderivative, as some people say, is the natural log of x. And let's evaluate that from 1 to 4. And when you plug that in, you get the natural log of 4 minus the natural log of 1. The natural log of 1 is equal to 0. And so we just get the natural log of 4, which again is saying, if you look at this graph of 1 over x over here, kind of looks like that, and it asymptotically approaches y equals 0, and you looked at it from 1 to 4, this area is equal to the natural log of 4, which is something slightly bigger than, the natural log of 4, maybe a little bit bigger than 1, right? 4 is e to what power? Something like that. Okay, and again, this is how you do for a definite integral. It doesn't get any different if these functions are more complicated. When you do a definite integral, you are bounding it, lower bound and upper bound, which are telling you typically the x's, when to start and when to stop. The integral is equal the area under the curve, which is the accumulation of that rate. You can start at negative values and go to positive values. What would happen if you would flip those bounds? And so, just to be clear, the integral from like a to b is just going to be the opposite of the integral from b to a. And hopefully you can see that if you just flip those things, you'd flip those things, and you're going to subtract the other one, right? 10 minus 5 is the opposite of 5 minus 10. So you can do stuff like that. You can use symmetry sometimes. So there are other things that you need to explore, but kind of the basics of the definite integrals is right here, and then this is kind of like the formal definition of it.